Welcome to qnawire.
From problem 25, we know that the tangential acceleration vector is equaling the cross product between the angular acceleration vector and the position vector r. For this object specifically, rotating counterclockwise and gaining angular speed, we can say that the angular acceleration alpha here is going to be equal to the magnitude of the angular acceleration in the k hat direction. And so here, the tangential acceleration would be again equaling alpha cross product with the position. This would be equal to the determinant of the following 3x3 matrix, I hat, j hat, k hat, and then we have 0, 0, alpha, and then we have r cosine of theta, r sine of theta, and 0. This is giving us negative alpha r sine of theta I hat, and then plus alpha r cosine of theta j hat. And so for part A, we need the acceleration in order to calculate the torque vector, which we know to be the cross product between the position vector and the force vector. And so we know that the force consists of two components, the radial tangential component. There's no torque associated with the radial component because we can say that the angle between the position vector and the centripetal force vector is going to be 180 degrees. Therefore, they're essentially parallel to one another, but in the opposite directions. So that means that there is no force associated with that radial component. And so we can say that then the torque vector is going to be equaling, again, the cross product between the position vector and the force vector, and this would be equaling the cross product between the position vector and the tangential component of the force vector. This is going to be equaling the position vector cross product with the mass times the tangential acceleration vector, and this would be equaling the mass times the position vector cross product with the tangential acceleration vector. And so the torque is going to be equaling the mass, and then this would be multiplied by the determinant of the following 3x3 matrix. We have I hat, j hat, k hat, and then r cosine of theta, r sine of theta, 0, and then negative alpha r sine of theta. Then we have alpha r cosine of theta, and then again 0. And so the torque vector would be equaling the mass times r squared alpha cosine squared of theta I hat. Rather, my apologies, just cosine squared of alpha, and then plus r squared alpha sine squared of theta, and then the direction would actually be only in the k direction. We know that cosine squared of theta and sine squared of theta, due to the trigonomic identity, would just simply equal 1. And so the torque vector is then going to be equaling mr squared alpha times k hat. And so this would be our final answer for part A. For part B, we know that the moment of inertia of a particle is I equals m r squared. So the torque vector would be equaling the moment of inertia times the angular acceleration vector, and we know this to be equaling mr squared times the magnitude of the acceleration, the angular acceleration, times k hat, which is the exact same answer that we had found in part A. But that's how we would prove part B. That is the end of the solution. Thank you for